Hello everyone, and welcome to the live session on gradient descent by Professor Dinesh.
Sorry about that you have asked, and what we will do today, and also so the session would be fairly introductory in nature. So in that sense, we are not going to what do you say, doing gradient descent for a simple example and a slightly more complex example. And hopefully things should be very clear to you at the end of it. And if you have any further questions, do ask now or later. So we'll try to get back to you with the answers. Okay, so we'll start. So the questions, I'm going to answer it within the lecture itself. Right? So I'm not going to state the question and then answer and so on. So hopefully it will be clear to you as we go along, right? So that the session is a little cohesive in nature. Okay, so let's get started. So I'm going to share my screen and use the Wacom to write things, right? And later we'll also go to the code where you have a Jupyter notebook. Okay, so let's start. So here we are, and okay. Hello, yeah. So what are we going to do now, right? So we're going to talk about gradient descent, background, and implementation, right? And within this background, within the idea of background or motivation, right? We have four main questions that people have asked. So why gradient descent, right? Why gradient descent, or what is the motivation to talk about gradient descent at this point in time where we are actually doing linear regression, right? Then the second question is, okay, we talked about gradient descent as an iterative method, right? How is it different from, say, closed form method, right? What is closed form? And suppose you have ordinary least square method, right? So how is this these two different, or why use this versus the other, right? Closed form. Okay, so this is one main thread of question. And also one other thing is, why move when we talk about the gradient descent algorithm, why do we move in the direction of, right, direction of negative of gradient of a function, right? Suppose we have a cost function j and we take a gradient with respect to variable x. Suppose we have a function j of x, right? Now, why are we moving in the direction of negative of gradient, right? That's a question we should ask, so that justifies the gradient descent method, right? And then how do we choose? How we choose eta, right? Which is the learning rate, right? So these are four main questions. So many questions are actually addressed in this point, right? And then we'll subsequently talk about the other questions as well, right? So now let us move on to the first question, which is why gradient descent, or what is the motivation for gradient descent, right? So so if you think about the relationship between linear regression versus neural network, right? Or for that matter, logistic regression versus neural network, right? So neural network as regression, right, to neural network for regression or neural network for classification, right? So if you think about it, I mean, suppose you have variables x1, x2, and so on up to say xd, right? And you take a linear uh, combination, right? You take w1, w2, wd, right? And you sum up, right? And let's say you get y, right? So this is what is linear regression, right? Now, if you think about what a neural network is, it is nothing but x1, x2, etc., up to xd, right? But then you will have, say, here it is d, maybe here you call it h, d here, d dimension, h dimension, right? And Uh, so you do a linear combination like this, and then you also do another linear combination like this, and so on, right? Like this, you do various linear combinations, and then you apply what is called a non-linearity, right? Here, after the summation, so you do a summation, and then after that you apply a certain non-linearity. Okay, let's call it sigmoid function to start with, right? And then you have an output uh, like this, right? So the difference between linear regression and a neural network, which can do regression, right, is mainly what, right? You have introduced what are called hidden layers, right? And a hidden layer performs linear combination as well as a non-linearity. Then you get y, right? Suppose these are z1, z2 up to zh, right? Now y will be a linear combination of z1, z2, etc. up to zh, right? So what is the main point that I'm trying to make? A linear regression, as we have seen here, doesn't have any hidden units, right? Here you have one hidden layer, and you have hidden units, which are these, right? These are the hidden units, and then you combine this output to get y, right? So in some sense, what we have in the case of linear regression is a simple what is called a linear. Uh, it's a linear function, right? Whereas this is what is called non-linear. This is non-linear. This is linear, right? And so in the case of linear regression, right? So this is the relationship between linear regression and neural network. And if you want to ask the question, okay, how is logistic regression related to neural network, right? So what will happen is very simple. So in the case of logistic regression, right, the network almost looks similar, right? X1, X2, etc. up to XD, right? So you still have something like this, right? You take a linear combination. So here at the output node, you have not only summation, right? You also have a non-linearity, right? So in terms of a simple dot product sort of representation, right? So we could write W1 x1 plus W2 x2 WD xd, right? So here, so this means y equal to W transpose. So W is a vector which is having elements W1 to WD, and x is another vector. So you can write it as a simple dot product like this, right? Now, what do we see here in the case of logistic regression? It will have a sigmoid operation after you do W transpose X, right? So if it is linear, you have something like this. If it is non-linear output unit, which is logistic regression, you have something like this, right? So this is useful for classification. This is useful for regression. And from here to here, what did we say? So this is linear, right? This is non-linear, right? Similarly, one can start with logistic regression, which is essentially linear, and just the output alone is having a sigmoid nonlinearity. So this is linear, and you could have a neural network which can do classification. So you can just draw a diagram very similar to this what we had. Only thing is, at the output you finally say there is a sigmoid function. So you go from linear to non-linear, right? So this is in terms of the model, right? In terms of model, right? We have four models: a linear model used for regression, a non-linear model used for regression again, uh, a linear model used for classification, but you have the sigmoid nonlinearity at the output, and finally a non-linear model which can do classification, right? We have four such models, and we also know we have this notion of a cost function, right? Right, and you will see later, right? So you will see that for the case of regression, what is the cost function? You already know it. For classification, you will see what is the cost function later, right? For regression, it is nothing but the mean squared error, right? Mean squared error, right? So this is the cost function in the case of regression. In the case of classification, you will see later that we will try to do what is called you will use an approach called maximum likelihood. Right. So this we will talk about later. Maybe when you come to logistic regression, you can look at this carefully. So what is the point that I'm trying to make? So 2 points I'm trying to make. One is in terms of model. We have seen models, different models, and how linear regression is related to neural network, which can do regression. How logistic regression is related to neural network, which can do classification. Right. So this we know about model. Now we should talk about cost function, right? And so the main point that we said is, okay, for regression we use mean square error cost function, right? So one interesting thing that happens both for the case of linear regression and logistic regression, right? Uh, the the cost function, right, for both linear and logistic regression, right? It happens to be what is called a convex cost function. We don't have to go into mathematical detail about convex cost function. We can just, what do you say, just have an imagination for how it will look like, right? It will look like this, right? So for the case of linear regression, you will have a cost function which looks like this. Suppose you have x, so this will be j of x, right? So it will look like this. For the case of logistic regression, where we try to maximize the likelihood, so you will have a function which becomes maximum at some point, and that is a parameter that you are looking for, right? So you will have a cost function which looks like this, right? So this is convex, and this is concave, right? So what do you observe about this now? The observation is, when you try to minimize this function, find the point x where this becomes the least or this becomes the highest, right? That's unique, right? So you have unique minima or maxima. Now the question is, are there situations where the cost function may not be like this, right? So what could be, where could we see such cost functions, right? So an immediate answer is, so for the case of neural networks, right, the cost function is not convex, right? So let me go to another page. So the cost function for neural network is non-convex, which means that it can have multiple what are called local minimas and one global minima, right? So in that situation where you have neural network with multiple local minima and just one global minima, the question is, okay, if you have a method which can only find a local minima, right? You will be getting stuck in a local minima, right? So let us try to draw one cost function which say looks like this, right? So this is what is called the global minima. So this is x, and this is say j of x, and this point, let's say this is the global minima, xgm. At this point, the function becomes as the lowest value, right? Now there could be other points like this, which are local minima 1, x local minima 2, right? So where can we come across such a cost function? So this week we will come across in neural networks, right? So the main point I also wanted to mention was gradient descent. Gradient descent we will be talking about in more detail um, when we talk about neural networks. Okay, so it is not that this is the only time we will be talking about gradient descent. We will be talking about gradient descent in full extent when we talk about neural networks. Now the question is, why did we introduce gradient descent at this point, right? What is the whole point in introducing gradient descent, right? So maybe a quick sort of graphic could help us to talk about why we introduced gradient descent now. So we have linear regression, logistic regression, which we will come to later, and then we have neural networks, right? So the point is, in terms of solving, right? In terms of, uh, so we have talked about cost function, right? Now let me make it into red so that it's little emphasized, right? So we have talked about model, we have talked about cost function, right? Now we need to also talk about what are called optimization methods, right? So within optimization methods, right, we want to sort of distinguish between two main types, right? One is what is called the closed form optimization, right? And the other is iterative iterative techniques, right? Iterative techniques of optimization, of which iterative itself, there are two types, at least two main types, right? One is gradient descent, which is a first order method. What we mean is first order is we compute derivative, the first derivative, right? Which is the gradient, and we try to move in the opposite direction to the gradient, right? Whereas you have also what are called second order methods. So Newton's method is an example of second order methods, where we might be starting to see terms like this, right? So we are not majorly focusing on this part, right? So we are not focusing on the second order method. We will primarily be focusing on the first order method. Somebody asked, are there any other iterative methods? Yes, there is another iterative method, which is the second order method. And if you have time, do have a look at Newton's method also, right? So now, as we said, we have iterative method, which is gradient descent, which we will talk about subsequently. And then there are also what are called closed form methods, right? Closed form method is something that is quite simple, where we just say at a minima. So we know that you have a minima, then you put the gradient is 0, and then you try to solve, right? Solve after this. So if you have two variables, you might get two equations. Just solve them. You will get say suppose you have slope and intercept, right? So if you have two equations in m and c, so you will be able to find out what m is equal to and c is equal to, and you will get an answer in one shot, right? This is one shot. Solve two equations, get the answer. That is what is the closed form way of doing things, right? Now, I mean, so now we will be talking about gradient descent, and yeah, I'll complete this picture for you. So you have the closed form, you have gradient descent or Newton, right? So interestingly, what happens is for linear regression, as we said, it is a cost function which looks like this. It's a convex cost function, which means that there is global minima equal to global local minima, right? Is equal to local minima. It has only one minima, right? So for the case of linear regression, the cost function looks like this, right? And it's a convex cost function, and you can actually use closed form method, which we have done in the lectures, right? You can use closed form method to find say m and c, which will fit a set of data points, right? So you have data points like this, and you would like to fit a model like this, right? So suppose this is the axis, this is x, this is y, and each of these points are xi, yi, right? They have a certain x value and a certain y value, right? That's why you have xi and yi. So these are green points are given to us, and we would like to fit a model. So we end up finding what the line, which is a blue line, is. So basically, we estimate m and c, right? Either m and c, or you can call it beta naught. Say the equation looks like this, beta 1x, right? So you find beta naught and beta 1, right? So for this type of problem, right, you can use closed form. You can solve it using closed form, and you will basically get one shot solution in one shot. And you can also use gradient descent. You can also use Newton's method, right? All options are possible, right? These two are iterative methods. In the case of logistic regression, you will see that a closed form solution is not possible for logistic regression, and you have to use either gradient descent or Newton's method, right? So we will see that when we come to logistic regression, it so happens that you have a cost function which looks like this, and in order to find out this point where you get the global maxima, right, you have to use gradient descent, right? And later, when we go to neural networks, right, we will see that I mean the difference between gradient descent versus Newton, right? Newton is fast, right? Whereas gradient descent is slow, right? Second order method, Newton's method, is fast, whereas gradient descent is slow. At the same time, Newton's method is compute heavy, right? This is light, right? So in that sense, there are pros and cons between gradient descent and Newton's method. Now, depending on your cost function, you can choose which works for you. So in the case of neural network, it so happens that the number of parameters, right? The number of parameters, which is nothing but the weights, right? The weights in the neural network are large, right? So which means that to use second order method, you will have to it will become even more heavy, right? When you have many parameters, to do Newton's method won't be a good idea. So you might want to drop Newton's method and go with gradient descent, right? And anyway, the closed form may not be possible as well, right? So this is the larger picture. Why we are talking about gradient descent is because gradient descent will become the primary method that you will employ uh, to find out the best parameters, starting with logistic regression as well as in neural networks, right? And we will come back and address all questions related to gradient descent while we talk about gradient descent for neural networks. So we will do that subsequently, right? Whereas now, what we are basically telling is uh, it is very easy to understand how to find out the parameters beta naught, beta 1, m and c. In the case of closed form, it is very easy. At the same time, one can also introduce gradient descent here itself so that you are familiar with this, and you also have this notion, right, ready with you, that you have two options, right? One is so you have two options. So given a cost function, the mean square error cost function, you can go one way. In the case of linear regression, find m and c using closed form. You can also go another way, which is to use gradient descent, right? And how does gradient descent work? You initialize the parameters m and c with some value, right? And then iteratively you get to better and better m and c values, right? So now let us go ahead and talk about actual mechanics of gradient descent, right? With all this background, which is what I wanted to tell. Why we are looking at gradient descent is because this is the easiest place where we can introduce gradient descent, right? That is point number one. And going forward, you might gradient descent will become like the workhorse for you, right? It will be the main workhorse which will do the learning problem, right? To do learning where you will have input as the training data, and output of the learning process is the so the output of the learning process is the uh, the output of the learning process is the parameters, right? So gradient descent will become the workhorse, right? So now let us go ahead and talk about the mechanics of gradient descent. So before going there, just one quick point. So in the case of so somebody had asked, okay, for linear regression, we have this cost function. For tomorrow, if we have another problem, right? How do I define that define cost function for that problem, and how do I solve, right? So I mean, for all practical purposes, right? What we will end up doing, right? We will end up mainly looking at problems of two types, right? One is regression, and the other is classification, right? And for regression, right, mean square error is a good cost function, and for this we will be talking about in the case of in the case of logistic regression, what is called the maximum likelihood, right? So as long as we know that our problem is regression, we can use this cost function. We know problem is classification, we can use maximum likelihood cost function. So if somebody is a little purist and want to sort of ask a related question, right? Which is, oh, I haven't seen maximum likelihood cost function in the case of classification. You might have seen what is called cross entropy, right? Which is a notion very much related to the maximum likelihood, right? So at least if not maximum likelihood, you would have seen cross entropy. And these are two standard cost functions that you will use in your applications, right? And you will also just for your being comfortable, right? So you will have standard cost functions. So you will have some standard cost functions from which you can pick and choose, right, depending on what your problem is. And you will also have what is called automatic differentiation, right? So usually toolboxes will have this facility. So you can just give it saying, okay, I will use a mean square error cost function. You tell me, you compute the toolbox will compute the gradients, right? And then you can use the gradients in the gradient descent method, right? So, or sometimes everything is, the whole thing is a black box, right? And you don't even have to think about it. You just say it is a regression problem, solve for the parameters, or classification problem, solve for the parameters, right? So you will be operating at a level of abstraction where you don't have to worry about it so much. But at the same time, I think we should be aware of what goes underneath. So we don't want everything to be completely black box, right? So at least we should have some understanding of what is happening, right? So we should be we should know, okay, for regression maybe this is the cost function, classification this is a cost function, and you'll use typically gradient descent inside. So we have some idea of what is going on. Maybe tomorrow when you want to go dig deeper and change things, maybe you can start to do that also, right? So that's a main question. So don't worry about cost function so much. Also differentiating so much, right? What we want to show is for very simple functions, if you end up actually solving it and so on, you will later be able to appreciate, this function that is the learning algorithm is actually doing this, right? So you'll be able to appreciate it better. Okay, so gradient descent itself, right? So we know how the algo works. So you have parameters, say w new, and you have w old, and you do this, right? You have a cost function j. You do this at w equal to w old, right? So what do? What is the basic logic? You compute the gradient. You compute the gradient at the point where you are, and you move in a direction which is negative of this gradient multiplied with some scale factor, right? That is what this means. So now let us try and illustrate this for the case of a simple function like x square, right? So you have So you have a function j of x, and you have x. Now let's say you are at this point, right? So the function value is something, and you are at a initial point, let's say x naught, right? Now what will you do? You will compute the gradient at x naught. What does it mean? You do a differentiation of j of x, right? And x equal to x naught, right? So for this function, if j of x is x square, then if you differentiate with respect to x, you get 2 times x. So this you know, right? If you have a polynomial x power n, differentiate is n x power n minus 1. So don't worry about, oh, if I got my differentiations and so on, that's fine. Here, we just take a simple function and differentiate and so on to show that this is what is happening, right? So it's not that we're going to test you on differentiation and all that. Okay, so given that j of x is x square, we have computed the gradient. Now we have to compute the gradient at x equal to x naught. So suppose x naught happens to be say 10, right? We are at 10 here, right? Now, how does the algorithm work? So x1 is equal to x naught. That is where we are. Eta is what is called the learning rate. I'm going to give all the intuition for these two questions, right? Why move in the direction of negative gradient, and how to choose eta, right? So these two questions we'll address. Now we'll just assume that we are moving in the direction of negative gradient, and we have a learning rate which has been already chosen, right? So suppose eta happens to be, let us do two things, eta with 0.1 and eta with 0.4, right? So let's start with eta equal to 0.1. So let us, so this is what, right? This is what we should do, right? One step of gradient descent. So we are now at 10, and we have chosen eta as 0.1. And when we compute the gradient, we got 2x, right? And 2x at x equal to 10, right? So 2 into 10, right? So this happens to be what? 8, right? So what has happened? So we were at 10, right? Now we have moved to 8, right? So like this, if you keep taking one more step and move, right? Suppose you do once more, right? x2 equal to x1 minus eta times jo x equal to x1. You do that. So what do you get? You are at 8. 2 times 8, right? So you get 6.4, right? So now then you move to 6.4. So what is basically, what are you doing? You started with some x naught, you move to some x1, you move to some x2, and so on, right? So this is how the algorithm works, right? So it's an iterative procedure to arrive at the local minima, right? So the question is, okay, why do we move in the direction of negative gradient, right? So by looking at this, you might have got some idea, right? Suppose you are at this point, which is here, right? Just imagine, I mean, for this particular equation, you have only two choices, right? You are here, you can move this way or this way, right? And just imagine if you actually move in this way, what is going to happen? If you move in this way, the function is going to increase, right? Whereas if you move in this direction, the function is going to decrease, right? So this is the main difference between the case where you have when you move in the direction of gradient and when you move in the direction of negative gradient. So so if you want, we can just do it as well, right? Suppose we move in the direction of positive gradient, right? What happens? 10 plus 0.1 into 2 into 10, right? So you get 12, right? Basically, you have increased the function, right? So basically, the gradient tells you in which direction, if you move, the function is going to increase the maximum, right? Now, if you move in the opposite direction, you're going to move in a direction where the function will become as minimum as possible, right? So here it is very simple. There are only two directions. Now we can use this knowledge to start talking about, say, 2D functions and more parameters and so on, where it becomes very clear, right, how the gradient descent is going to work. Now let us think of a function like this, where you have m, the slope, the intercept, and then the cost function, which is a function of m and c, right? And suppose it so turns out, I mean, just for our simplicity, let's say that it looks like this, right? Which is just 2D extension of x square. So suppose this looks like this, right? M square plus c square, right? So you will see that, I mean, you have some sort of circle at every level of the function, right? Now, if you try and visualize this in 2D, right? How could you visualize? Maybe think of doing a top view from here, right? What you will see so you will see concentric circles, right? And here is where the function is going to become minima. So as you can see, because it's sum of two squared terms, right? The when you when you try to find the minima of this, it will be a point where m equal to 0 and c equal to 0, right? Just like you had x square, you will get m equal to 0, c equal to 0 as the solution. Now just see what happens. So now what we are doing, so this is the case where the j of 0 comma 0 is 0, right? So this is the point where it is minima. And as you say, look at, say, m square plus c square equal to, say, 1, right? You will get a circle, right? Similarly, m square plus c square equal to 4, you will start to get another circle, right? So when the cost is 1, when it is 0, right? So this is a point, this is a circle, this is another circle, and these are concentric circles, right? So you can actually visualize the cost function equal to some constant, right? As concentric circles, right? So you can visualize it like that. Now, what is the gradient descent doing, right? So let us look at gradient descent in this case. Maybe you are at a point which is 10, 10, right? Now, if you try to find the gradient, what is going to be the gradient, and in which direction should we move, right? So if you find the gradient for this function, so how do we find the gradient? Dou j by dou m. This is one element. The other is this element, right? So if you denote the gradient by this, so this is a definition. J is a function of m and c. Now, if you take a gradient of this function, you have to do partial derivative with respect to m. You have to do partial derivative with respect to c, right? So this is, so you make it into a vector. It looks like this. So this is the definition, right? Now let us. So as we know, if you have to write gradient descent in this case, how will it look like? So it will look like this, right? M new and C new. M old, C old, minus eta times dou J by dou M, dou J by dou C. You evaluate this at the old parameter value, right? So that is what gradient descent for 2 dimensions looks like, right? 2 dimensions. Now, let us say, so we are assuming that this is 10, 10, right? So we are starting at 10, 10. Now, if you take one step of gradient descent, where will we reach, right? So what will be our M new and C new? Maybe you can do it yourself. So there are 10 and 10. Suppose, so I'll come to this point about eta subsequently. So here also, let's say eta is 0.1. Now you say this is 0.1, and differentiation of j with respect to m. So your cost function j of m comma c is equal to m square plus c square. Now if you differentiate with respect to m, c is a constant, so this is a constant, you don't care about it, just write 2m, and dou j by dou c is equal to 2c. Now differentiating with respect to c, you don't care about m, so it just c square, so you get 2m and 2c, right? Now 2m and 2c, but evaluated at m equal to the old value, which is 10, and c is also 10, right? Now if you do this, what do you get? 10 and 10 minus 0.1 times uh, 20, right? Right. So what is the main point, right? Just look at this 20, 20, right? So if you look at this vector 20, 20, right, it is going to be a vector which is like this, right? So you are at 10 comma 10, right? So you are at 10 comma 10, right? Now, so this is the direction in which the gradient is pointing, right? Whereas if you take a negative of it, right, it is exactly pointing towards zero, right? It is the direction in which if you move, you will actually hit the local minima, right? So that is the intuition why you would move in the negative direction of gradient, because that is the direction which will help you to reach the minima fastest, right? So any other direction. So here you have various choices, right? So in terms of, right, so this is the best one. This is the direction in which the function will increase highest, right? Whereas any other directions, right, will not be as effective as a negative gradient, right? So the negative gradient is the best direction to move so that you can slowly reach the minima, right? So, the question, so why move in the negative gradient descent? Hopefully, is addressed now, just as an intuition, right? Uh, so, one question uh, as a side question somebody asked was, what happens if you have multiple local minima, right? So in which case, how will this method work, right? So the answer is very simple. If you have multiple local minima, depending on where you initialize, right, you will reach one of the local minima, right? So the method is such that once it sees a local minima, it will stop, right? We don't have to worry about that in our linear regression case, because the cost function itself is a nice convex function. It has only one minima, so you don't have to worry about the minima so much, right? So at the end, I mean, what is good to know is that our cost function, I mean, if your cost function has multiple local minima, then you have to be careful, right? So as we said, so in this case, you will reach here. If you have a cost function like this, then if you start from here, then you will reach here, right? So you start from here, you reach here. If you start from somewhere here, you will reach here, right? And so on, right? So that is what you will get as output, right? So now the another question which we didn't address is, so the choosing eta, right? So eta is actually an empirical quantity, or a quantity that we have to set. We have to set for our problem, right? So we can play with it and set eta. Maybe there are some rough guidelines for choosing eta, but it is something that we have to empirically find out what is the best eta for us. What we just have to need to be aware is when eta is large, you will see an oscillating behavior, whereas when eta is small, you might see that convergence is slow, right? Convergence to the minima is slow. Convergence is slow. So let us look at the case where we saw eta is 0.1, right? So when eta was 0.1, we started from 10 and we reached 8, right? And subsequently we started at 8 using eta as 0.1, we reached 6.4, right? Now the question is, okay, when eta is 0.4, what happens? So just to summarize this, so with eta equal to 0.1, we started with 10, we moved to 8, and then we moved to 6.4, right? That's what happened. Now, in the case where eta is 0.4, right? Now, what will happen? X1 will be 10 minus 0.4 times 20, right? So this will turn out to be 2, right? And similarly, if we try and compute x2, we will start at 2, right? And then we will take a gradient descent into 4. So we will reach minus 0.4, right? So how are things proceeding? So we start with 10. In the case of eta as 0.4, then we move to from 10 we move to 2, and then we move to minus 0.4, right? So what does this mean? In the case of eta as 0.1, we were like slowly moving towards the minima, right? Now in this case, how are things going to look like? So we start with 10, right? We quickly go closer, which is 2, but then we go negative, which is minus 0.4, and slowly we will so one has to evaluate the next step. Is it going to be closer or not, right? So at least one thing is clear. You see that there is an oscillating behavior here, right? You overshoot the minima and then slowly converge, whereas here you don't. In this case, we don't overshoot, but we might be a little slow in converging towards 0, right? So as I said, the main point is when eta is large, you see an oscillating behavior. When eta is small, the convergence is slow, right? So these are some of the main points. Hopefully addresses some of your questions. Now let us quickly move on to the code. So we have written, I think you have looked at this code already. Maybe I'll just quickly sort of go through it once, right? So this is something that is already shared with you, I think. So this notebook has 3 sections: gradient descent for a simple function x square, univariate gradient descent, compare it with sklearn, scikit-learn, so that you see what happens there. And so this is sklearn is like a black box, right? You don't know what happens inside. Whereas here you understand, okay, how could the algorithm work, right? You have a cost function, use gradient descent, what happens? Similarly for multivariate linear regression. So in the interest of time, I'll mainly go through the first and the second, right? And you can spend some time with the third one after this. So we have already seen the cost function x square, right? So let us try and do gradient descent for this simple cost function, right? So let us import some libraries. Let us try to take a range of x values, right? And so this is a range of x values we are interested in, and then y is nothing but x square. If you take a derivative, it's 2x, right? So let us, if you plot, so if you plot it, you get the function like this, y equal x square, and the slope looks like this. Now let us try and compute. Let us try and do gradient descent, right? So here is where the gradient descent algo is happening. It might look a little overwhelming. Oh, what is happening? So what you need to focus on to begin with is this is the x naught, or the current x, right? So it is 6, right? And learning rate is 0.01, right? So here it is a different learning rate, right? So depending on your problem, you will choose different learning rate. Maybe you will experiment with different learning rates, start with 0.1, 0.01, and so on. It all, see, there is nothing like a perfect choice for learning rate, because learning rate is what scales the gradient, and depending on how the scaling is for x, right? You might have to use different learning rate, right? So if you just make all features multiplied with 10, right, then the learning rate has also has to be multiplied with 10, or made bigger, right? So I mean, it has to be so if x is scaled, then your learning rate might have to be controlled, right? You might have to divide it by 10, for example. So it all depends on what is a x that you have. Now, what is the main line of code that we want to see? So you have this current x, which is nothing but learning rate multiplied by the gradient evaluated at the previous x. So previous x you have is where you will evaluate the gradient and then multiply with the learning rate, and that becomes your current x. And there are other variables here. What are they doing? So you have a condition where you run the iterations for a maximum of say 10,000 iterations. So that is what this condition says. And also till the difference in the x value, right? Suppose you get very close to 0, right? When do you stop? You keep on taking iterations, right? Either you stop when you have increased the maximum number of iterations, or you stop when it becomes very close. I mean, the change in the x value, which is what is captured by delta, current x minus previous x, that change becomes very, very small, right? So that is the precision. Whenever the delta, as long as the delta is greater than this precision, keep running. But once it becomes lesser, you stop, right? That's a stopping condition, right? So this is the code, and finally you get a local minima, which is close to 0, right? You have, the ideal is 0. It is very, very close to 0. So this is how the code looks for gradient descent, and there are some parameters here, right? Okay, so now let us look at the second one, which is gradient descent for the case of the housing data set, right? You might have already seen the housing data set, where you have the price, you have area, and various other variables, right? And so this same example you might be using later. So we might have to do some uh, yeah, so we might have to do some pre-processing, convert on yes and no's and all that to numbers, a few other data preparation steps. The main point I want to say is the following, right? So I think these are all fine. So now you have numbers, you might have to do some normalization and so on. Okay, so this is the main thing, right? So you have area is your, so you're only looking at univariate case, where you have area as the only variable, which is the x variable, and price is the y variable, right? So you have x and y, and you would like to do a regression, right? You would like to do a regression, you'll have slope and intercept parameters. Now, if you, how does one get these parameters m and c? Using gradient descent and scikit-learn. So you can do the plotting of this data, price versus area, and you'll like to get a straight line, right? That is what you want to do. For linear regression, as we said, you will use a cost function known as a mean square error cost function, MSC, right? So you have a cost function J in terms of M and C, and this is the uh, total cost, right? For every data point, you have a height which is coming from the data, from the training data. There are n such data points. For every data point, if you look at, there is a ideal height, and this is the model. Model is telling mxi plus c, right? So model is, I mean, how does the model work? You have xi, which is the place where you want to predict. You use a model, which means that you will compute mxi plus c. That is your prediction. There's a prediction, there's an actual. You take the difference, square it, and that is the error for every data point, right? Like this, you will have n data points, you have n errors, and that's how you get to this cost function. Now, like what we did before, right? Think of the example that we did before. We had m square plus c square, which is one cost function. Here is a different cost function. Now, if you differentiate this with respect to m, with respect to c, what is going to happen, right? So the whole thing, you try to differentiate with respect to m. So what is going to happen? 2 will come outside, right? And let us even put a 1 by n here. So 1 by n is missing here. So this is the total squared error. Just assume that we put a 1 by n here, which means that it is a mean square error. That is why you get a 1 by n here also, right? 2 comes here, 1 by n is there, this whole thing is there. Now, when you're trying to differentiate with respect to m, right, what happens here? So this is a constant, this is a constant, yi is a constant, c is a constant. Only this part is a function of m. And when you try to differentiate with respect to m, so think of this xi as a number, right? 2, let's say, minus 2m is what you have. When you differentiate with respect to m, you get minus 2, right? So this is why you get a minus xi. And similarly, when you differentiate with respect to c, everything is almost same, just that you will, when you differentiate with respect to c, you will get 1. And then this negative sign, you get a minus 1, right? So you have these two equations that will help you to compute the gradient, right? Now, so this is your gradient equation, right? So now you can, as we said, we can choose the learning rate, and then we can use it in the gradient descent computation, right? So I'll just sketch the main part, right? So what is the main part here? This is the main part, right? So you have m current and c current, and the new value of that will basically depend on the m gradient and c gradient, which are computed at the m and c, which was there before, right? So how does that work? So that computation is what is happening here, right? So you do this dou j by dou m computation, which is this equation which is implemented here, right? These two, right? And you can also compute the cost j of m and c for a particular value of m and c. And so once you, so this is the main block, right? The gradient descent block. And you might have some parameters which tells you how many iterations, learning rate, and so on, right? Which is exactly what we did before. Before, what we had was a 1D function. We have a 2D function. We can use gradient descent, and once we compute, we'll be able to see what happens, right? You start with this m and c, and slowly your cost is coming down, right? Your cost is coming down, and finally you get a reasonable, once the convergence is achieved, you get m and c as these new values, right? The cost has become 0.71. So your cost has come down, and this is the plot where you have the cost with multiple iterations is coming down, right? Now you can finally write the equation y is mx plus c, right? So this is our equation. So this is how our implementation of gradient descent for linear regression problem works, right? This is our implementation. Now just compare it with how the scikit learn function works, right? So what what is the main thing? So you have X, you have Y, few other steps, right? You import libraries and so on. Finally, if you see, the function is very simple. You just use a linear regression function, LR, so you instantiate it and then fit a linear regression model to this data X and Y, and you will be able to get print the parameters, intercept and coefficient, right? So this is one line of code where you take as input the training data, and you already have, you can compute MNC, right? And internally what happens we do not know, right? It is internal to this, right? So we won't know what is happening inside. Maybe we look at the help and find out, okay, what is happening inside. It can be closed form, it can be gradient descent, right? One has to really see what exactly is happening, right? So what is the message that we are telling? Yes, it's just not a black box. We can start to look at what happens inside. If it turns out to be gradient descent, this is how it looks like, right? A simple gradient descent computation, right? Now later when we come to logistic regression, right, we will extend this from for a regression problem to classification problem. We can use gradient descent there. So this was with MNC, where you have two parameters. When you have uh, when you do linear regression for multiple variables, right? Suppose it is not just price, but say area and bedrooms is also. So you have two variables. You might start to look at problems which are of this type, right? Where you have the output variable Y is a function of. So this is your C, this is your M1, this is your M2, and so on, right? You have multiple slopes, right, and one intercept, and so even in this case, the situation is very simple, very similar, right? Where so this whole thing, you can write it as a summation like this if you want, and you can also write it as a dot product like what we saw some time back, right? So if you write it as a dot product where you have theta, theta naught, theta 1, theta 2, etc. up to theta d, and the x's, you will see that because theta naught doesn't have its corresponding, say, x naught, right? So you can just put a 1 here, and you can create a vector out of this, and this is the vector that we are talking about, right? Before it was very simple, uh, mx plus c. Now you have more variables, and this is a neat way of writing it also. So when you have more variables, you can just write it as a dot product like this, right? So you will be able to with some time, right, you will be able to uh, I mean, if you write a cost function. So I can quickly do that if you think, right? So for the case of for this case, right, so you have your Y prediction is equal to h theta times x is equal to theta transpose x, right? So this is our predictor, and we have our cost function, which is MSC, mean square error cost function. So you have, let's say, if you have m samples, you have something like this. Right? So this is our cost function. So you have your prediction, which is this. This is the actual. So I put a yi, right? And now if you try to differentiate with respect to 1 theta j, right, of this cost function, you will get 2 by m I equal to 1 to m theta transpose xi minus yi, right? And uh, this is theta transpose xi is nothing but theta naught x naught plus theta 1 x1, etc. theta d xt, right? Now there will be one term which is, say, theta j xj, right? Now if you differentiate this with respect to xj, right, you will get sorry, if you differentiate with respect to theta j, you will get xj, right? So that is why if you differentiate this, you will get another term which is xj. And because we are talking about the ith data sample, we put an I as well, right? So this is how you formally differentiate the cost function, which is the mean square error, and then show that if you have to do gradient descent, you will have an equation which might look like this, right? So right, so something like this should make sense, right? So here they have left out the 2 times, right? So you can add 2 here if you want. Anyway, alpha is there, so it will absorb the 2, not a problem. But hope you see this structure is similar to what we have just seen, right? Where you have theta j. So this part is what is covering the gradient computation, right? The gradient computation has 2 by m times summation, 2 by m times summation, and h theta of xi is nothing but the prediction, which is a linear prediction here, theta transpose xi minus yi times, depending on, say, if you look at theta j, then you get xj, and superscript is I, right? So this is the gradient computation for the case of gradient descent when you have multiple variables. So I don't want to emphasize this part so much. I mean, this is just for those who are interested and want to also understand the multivariate linear regression part. So you will be able to understand this code and basically see that what is implemented is this in the code, right? So we'll leave it at that. Hope you got an overview of why gradient descent, what is the difference between closed form. Let me just stop sharing screen. Yeah, so hope you got a good idea about why we need gradient descent. How is linear regression related to neural network? Here you have a convex cost function. There you have a cost function which may not be convex. And then because we are looking at convex cost function, always you will, when we always do gradient, right? And how do you choose eta? If you choose eta large or small, what happens? And eta, choice of eta will depend on your problem. You might have to look at your variables, what is the scaling, and then choose eta, right? And then we now have a fair idea about if you actually write a code for gradient descent, how will it look like? You will have parameters, and you will have, if it is just one parameter, then one equation. If you have many parameters, many equations of computing the gradients. At the end of the day, gradient will turn out to be a number, right? Each of the gradient will be a number. You will start with the initial value of m and c, and you will add another set of numbers, add to I mean, as long as it if the change in parameter value is not much, you say I stop, I have found my local minima, and then you can close, right? So hope you got a good idea about the basics of gradient descent. For those who are sort of little advanced and want to pick up something more advanced, maybe you could look at the multiple linear regression model and the cost function and so on. But essentially, I mean, the code will, I mean, the scikit-learn library will help you to do all this. But this is just to make it not a pure black box, but sort of a gray box, right? You understand what is happening. And in other problem settings, if it is a regressional classification, you can continue to use the same cost function. You don't have to worry about the cost function. You don't have to worry about differentiation because the toolboxes will allow you to do differentiation. So in that sense, usually you don't have to go beyond the script usually. But for problems where a little bit more complex, more new or a different type of problem, there you might have to think of a new cost function and then to get to the solution using the new cost function, right? But usually you don't do that. Yeah. So we'll stop here, Sumit.
Yeah. Hi. This is Dinesh.
Yeah. So we'll stop here.